Hi guys, let's look into the another new concept, electrostatics of conductors. So this concept is something different. Till now we discussed about so much about the static charges. But when it comes to conductor, the things will gets different. Suppose if you take these two are the two different. So this plastic you can take hockey ball. So it's an insulator. So on this hockey ball, if I put a charge, suppose if I give negative charge to this hockey ball, so this negative charge will remains at here. So it will located at here only. So it do not change its positions. So it remains. But when you can take at this one, it says copper, a copper ball, and copper is a good conductor of electricity because it is having negative electrons. But when you can give a negative charge to this conductor, you are giving extra negative charge. So it means if I give a negative charge on this copper, so if I give the negative charge at here, now things won't be same as like at here. No, since it's a insulator, non-conducting material, the electrons won't affect on the others. But since it's a metal, this electron will affect the electrons which already present in the copper, because copper contains a good number of free electrons. Now these two charges and they repel each other, they can apply certain force and so many things get happens. So that's why this concept, especially the concept what we are dealing at here, the electrostatics of conductors. So that is different because when external field is applied on a conductor, or when you can keep a conductor in an external electric field, so that external electric field makes certain tremendous changes in the conducting material. So we will discuss electrostatics separately for conductors. So let us dive into that first. To make you for better understanding, here I need to take one definition, that is electrostatic equilibrium. So this definition says, suppose if it's a conductor, you can take a conductor just like a copper. So it's a charged conductor. It means you already given that a charge on the conductor. So by the time what happens, if a charged conductor, the excess charge, the excess the excess charge has optimally distanced itself so as to reduce the total amount of repulsive force. Once charged conductor has reached the state, this state is known as electrostatic equilibrium. There is no further motion of charge on the surface. So that definition says about, suppose if you can take this copper, if you can take this copper material. Now on this copper material, if you can give an excess charge, now on this copper material, if you can give an any x charge, suppose if you can give as a negative electron. Now what happens according to this definition? Now this excess charge has optimally distanced itself. Suppose if you can give at here 1 nanocoulomb of electrons, it's having 1 nanocoulomb. of electrons. So that 1 nanocoulomb of electrons, those all electrons will separate by themselves. Why they separate them by themselves? Because all are having negative charge. So all the charges they separated quickly, as we can say that time as infinitesimal time. It takes around 10 power minus 9 seconds within that time. So those all entire excess charge will distributed equally all over the surface of the conductor. So if that happens, now the conductor is at a particular state, so that state we define as electrostatic equilibrium. Once the conductor reaches to this state, electrostatic equilibrium, there is no further motion of charge about the surface. So this we will take as a general property for the conductors, as simplest as a duck soup. It means if you can give a charge on a conductor, what happens? That conductor having electrons, now those electrons will be carry the charge, so that charge entirely equally distributed all over the conducting surface within the fraction of time, and it reaches a state which is known as state of electrostatic equilibrium. Once the conductor reaches to that state, now there is no further movement of charges. Now if any conductor charged, if you take a conductor and give a charge, so quickly the electrons occupies all over the surface within the fraction of time, and it reaches to a state which is known as electrostatic equilibrium. Now by taking that, so let us see one by one property. So the first one at here, which is given there, inside a conductor electric field is 0. Inside a conductor electric field is 0. Let us see that first. Suppose if you take a conductor in an electric field, it's a conductor. We are not talking about any kind of insulator. Suppose if you can take, this is the conductor. So this conductor we kept in an external electric field. So here I am having a positive charge electric field. So I kept this conductor in an external electric field. So the electric field line shows they are in this along this direction towards, if you can take, that is the east direction. Now since it's a positive charge and conductor is a close to positive charge, so you can guess, so at here, so the electrons will occupy too close to the positive charge on this side. It means over the entire surface, all the electrons, they wants to move towards to the positive charge. So now if electrons wants to move, so they only move in the conductor. The positive charge they cannot move, since positive charge is a nucleus. It cannot move, only electrons will move. So electrons will move within the conductor towards to one side. So if the electrons move towards to the one side, obviously we can see there is a deficiency of the electrons, or we can take that as a positive side. So now this side positive charge appears to accumulate, because the total electrons came towards to the external positive charge. So this is as an external. Now here you can see within the conductor separation of the charges. So positive charge to negative charge. Suppose if I draw electric field line within the conductor, so electric field lines I need to draw from the negative to the positive. Now Within the conductor, if you can observe, there are the two electric field lines. One is due to the external, so these green ones are the external, and the yellow ones, they are the internal. Now within the conductor, the external electric field and internal electric field, they both are in equal and opposite. So what happens? The electric field within the conductor, that will becomes 0. So here you can write the electric field E equal to 0 within this conductor. So since the conductor is all over the space, now if you can take that conductor is all over the space, so within the whole the conductor, the electric field will be equal to 0 because of the presence of the external electric field causes charge separation. So here this charge separation we especially termed as polarization. We will discuss about that in the coming concept. So right now here the charge separations within the conductor, since here you can see only one dimension, but we have to imagine that as a 3 dimensions. So in the 3 dimensions, the electric field within the conductor is equal to 0. Okay, so that's the first concept what we need to discuss for the electrostatics of conductor. Inside a conductor, the electrostatic field is 0. So here I hope you are getting one more doubt. So what happens if you take this is a conductor of a hollow, a solid or a hollow. If you can take any type, whether it is a solid or whether it is a hollow sphere or a conducting material, so the same property will be holds at here. So within the conductor, the electric field is equal to 0. Now let's see another concept for the conductors, electrostatics in the conductors. Second point, at the surface of a charged conductor, electrostatic field must be normal to the surface at every point. At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. Now if you can take a conductor, so that is so the same conductor, charged conductor. Now if you can take this copper as my conducting, and now this conductor is charged. Suppose let it be as an positively charged. So at here, so it's not visible. If you can take yellow, so this is the positively charged conductor. Now if it is a positively charged conductor, I need to draw the electric field lines. So how we can draw the electric field lines? We will draw the electric field lines at here. It should be normal. It should be normal at here. Or for the any conducting surface, if you can take that, so they all should be normal to the surface. Normal to the surface. So let's think like this. What would happen if the electric fields are not normal to the surface? What would happen? Suppose if I imagine that to the surface, these electric field lines are not normal. So let me take off electric field lines, just a tangent surface. Suppose this is the, if I can imagine that, so this is the electric field lines due to these ones. Now if I imagine like this, now what happens? This electric field is a vector. Now this vector, now we can resolve into the two components. If that is the field vectors, now if I can able to resolve, so as a horizontal component, Now if you can take that as a coordinate axis, one is the horizontal component. If you can take that, so if this is the y-axis and if this is the x-axis, now this electric field vector is now resolved into the two components. One is the horizontal component and one is the vertical component. Now if any of the component, electric field is having two components, one is the perpendicular component, one is the parallel component. If any of the component will interact the excess charges within the conducting surface, now that causes the movement of the charges. So this situation happens if we imagine if the electric field is not normal to the surface. If you can take the electric field as any tangent, so that causes electric field component will interact with the charges. Now if the electric field is interact with the charges, so what happens? The electric field applies a force. So this is the electric field versus force relations. So this force of applied on a charge. So again what happens? The charge will move. If the charge will move, we will miss the concept of the electrostatic equilibrium. So this concept we will miss if we imagine that the electric field is not normal to the conducting surface. So this concept will always as a property for the conducting materials. We can take that as a property. So that property violates if you can take the electric field component is not exactly the perpendicular to the surface. So we will treat that as the electric field is always perpendicular to the conducting surface. So that's why we used to draw the electric field lines for a conducting surface. So they will be moved for a conducting sphere from the outside. Now that is the second property. Now let's see the third one. The interior of a conductor can have no excess charge in the static situation. So how we can discuss it? You can see the interior of a conductor can have no excess charge in the situation. If the interior do not having where the charges is present, so that we can see. Suppose if you can take the same, now if you can take the conducting sphere, let me make a space. Now if this is the same conducting sphere, now if you can give a charge, let it be a negative charge. Now according to the electrostatic equilibrium conditions, what happens? This negative charge within the fraction of time, it will spread all over the surface. And where it will spread? So it will not present at the interior. Interior means you already know, which is not present within the inside. So it will present only the exterior. It means we can say the charge only accumulated on the edges. So here I have taken the negative charge. So the same negative charge will be located at here on the edges. So like this. So just like this, the charge, entire charge is distributed evenly. Now, so if I want to confirm what is the, how can I come to know that there is a no charge which is present at here? So the one and only the law, Gauss's law, that help us. So according to Gauss's law, the closed integral of E bar dot ds equal to q by epsilon naught. It means, suppose if I take a Gaussian surface, so just close to the charges, if I take a Gaussian surface just close, not on the outside, just there. Now, in the previous case, we learned that electric field which is inside, that equal to 0. So that we already proved. So in the earlier case, we discussed that here the electric field. So this is the case. The electric field within the conductor. So that goes to 0. Now, if the electric field equal to 0 in this case, so we can conclude that from this left hand side, this electric field E equal to 0. So that's supposed to be on the right hand side. In this q by epsilon naught, something should be 0. So in the q by epsilon naught is permittivity which is not equal to 0. Obviously, the charge q equal to 0. So if the charge q equal to 0, that it means, so within this Gaussian surface where you want to find the electric field, so that electric field becomes 0. That gives an evidence that the charge equilibrium property, electrostatic equilibrium property, when if we can keep a charge on conducting surfaces, so the charge will be distributed on its edges, a particular word if we can take it. So it will be uniformly distributed. Now, with the help of that evidence, we can conclude that electric field within the conductor equal to 0. Suppose if you want to find the electric field at exterior. So if you want to find, I want to find the electric field at the location. Suppose this is the location, if you can take it. Now this is the distance at a distance of r. So this is the at a distance of r. So you would like to find the electric field. Now here, so this is my black Gaussian surface. And we know how to find out the electric field. So we can find out the electric field. So closed integral of E bar dot ds which equal to q by epsilon naught. Now we can apply what is the surface integral if you can take it. So at the electric field, so the closed integral of E dot ds equal to q by epsilon naught. So to find out that, so electric field closed integral of the ds equal to q by epsilon naught. So it's form of a sphere. So we can find the electric field at exterior. So E times that equal to that becomes to me as 4 pi r square. 4 pi r square times q by epsilon naught. So the electric field at exterior, q upon 4 pi r square epsilon naught, which equal to 1 over 4 pi epsilon naught times q by r square. So that is the electric field due to this sphere at the outside, which is not inside. Now we can calculate the electric field outside because the charge is now within the Gaussian surface. But when it comes to find the electric field within the surface, the electric field becomes 0. Why the electric field becomes 0? There is no charge on that surface. So where is the charge? According to electrostatic equilibrium, the charge is distributed on the edges. So if you can read this properly, if you can understand that, so there is no net charge at any point inside the conductor. So any excess charge must reside at the surface. So for conductors, if you can give an external charge, now that charge will be resides at the surface. It won't remains where you drop. Now let us see the next point. Electrostatic potential is a constant throughout the volume of the conductor and has same value as inside on its surface. The fourth point is electrostatic potential is a constant throughout the volume of the conductor and has the same value on its surface. Now in this case, if you can take, we need to bring the relation between electrostatic potential. So that's very easy. Since we know the relation between electric field and potential. So what is the relation you can give electric field and potential? So if you can write the relation. Now the electric field and potential relation, if you can take that as electric field E equal to negative of dV by dr. Now it is means potential per meter. That's the relation between electric field and potential. So here it is having the special units, that's called volt per meter. So volt per meter is also electric field units. Now the negative sign shows about the direction of the electric field is the where the potential decreases. So that is the relation between electric field versus potential. Now here on the surface we are saying that electric field equal to 0. If the electric field equal to 0, so we know from the differentiations the derivative of a constant, so d by dr of a constant, so constant differentiation goes to 0. So here which term is the constant? So here the constant term is nothing but potential. Now if you can take any location within the surface, so the potential V equal to constant. So whether you can take deep inside or you can take on the surface till the edges on the surface, so the potential remains constant. So this potential constant due to because of the electric field becomes 0, that's on the surface of the conductor. So that we understood by the help of the electric field versus potential relation. Electric field E equal to negative of dV by dr. So here r is nothing but the distance that we can understand by remembering the potential electric field units in terms of potential. Potential per meter. Now in this case we are saying that on the conducting surface electric field equal to 0, so it means the potential remains constant. So that's the another property what we can see at here. Now let's see the another property for the electrostatic conductors. Electric field at the surface of a charged conductor. This is the formula for electric field at the surface of a charged conductor. Now, so the electric field at the surface of a charged conductor E equal to sigma by epsilon naught. Let's derive that. So for that, let me take a positive charged conducting surface. So to find out the electric field on the conducting surface, so what is the expression for the electric field for the conducting surface? So let me take a conducting surface, so which is having sigma. Here sigma equal to the surface charge density, so it's having a sigma surface charge density. Now to find out the magnitude of the electric field on this conducting surface, so the magnitude of the electric field on any conducting surface equal to sigma by epsilon naught, and n cap is the normal direction. So to prove this expression, so we need to consider a Gaussian surface. So here I have taken a cylindrical Gaussian surface. A cylindrical Gaussian surface. Now you take the situation just like cloud. So a positive charged cloud is there, and you kept a cylindrical Gaussian, a open cylinder, on two sides that you immersed in the cloud. Now since it's the positive charge, the electric field lines, they will pop up from the surface, so that is the direction of the electric field lines. So this is the direction of the electric field lines, and we learned that electric field inside equal to 0. Otherwise we need to draw the electric field lines from here also. So in this region, so the electric field is equal to 0. Now the electric field is equal to 0. Suppose if I take a Gaussian surface, so at here a cylindrical Gaussian surface. Now if I draw two more lines to make you understand. Yeah. Now if you can take the electric field, so within right at here, from the surface the electric field lines are moving the upward direction. So this is the electric field through the north. So this is the outside area, so which is the outside. Now from the downside, so the electric field equal to 0. So in this locality, so in this side, since the bottom of the cylinder which is inside the cloud, so we already arguing that, so there are no charges which are the present inside the conducting surface. Whichever the charge is, that is should present on the outside only. Now if there is no charge, there is no electric field, so I can claim it here the electric field is equal to 0 from this side. If you can name it that, from surface 1 and the surface 2. So electric field from surface 1 equal to 0 because no charge. And if you can take the electric field for this, in this curved surface 3 and curved surface 4. So if you can mention, this is the curved surface on this side. So on this curved surface, if you can take the electric field, so this is the curved surface on this side and the other side. So on the side 3 and side 4. So on the side 3, that is electric field is perpendicular to the curved surface area. So E dot ds, so we can take E ds cos 90 degree. So this value will become 0. Therefore electric field on the third surface and electric field on the fourth surface, this is also will become 0. Now on the three sides, electric field 1, electric field 3 and electric field 4. So on the three sides of this Gaussian surface, the electric field becomes 0. Now only one surface is left. So that is the electric field due to this, the second surface. Now if you can find the electric field due to the second surface, what you can write? We can write that electric field E equal to integral E bar dot ds integral E bar dot ds which equal to q by epsilon naught. Now here what we can write that, so here the q is nothing but surface charge density. Suppose if you can write that E times closed integral of the ds which equal to q by epsilon naught. So this we can write that as, or if you can convert the q in terms of the sigma, surface charge density. So sigma equal to charge per unit area, so q equal to sigma times a. Okay, now if you can convert that surface area E times a, the surface integral if you can take as a total area as a, and in the place of the q I can write that sigma times a by epsilon naught, and the area gets cancelled. You can get the final expression electric field E equal to q by epsilon naught. So that is the only the electric field which is coming out from the cloud, from the top surface. And if you can mention that it's a unit vector, suppose here you can take n cap, normal is the unit vector direction, so that is the n cap will be the unit vector direction. So from this property we can understood that, so the electric field at the surface of a charged conductor, electric field E equal to sigma by epsilon naught. Now the next property is known as electrostatic shielding. So to prove electrostatic shielding, consider a metal surface. So inside the metal surface, so I have taken a cavity. So here if you can observe, a cavity means a small air bubble space, means in that location, so there is a no metal, just like our tooth cavities na. So there is a hole. Now if the hole is present inside a metal, now that metal is kept in an external electric field. So here this positive charge gives to me the external electric field. Now this cavity metal is kept in an external electric field due to, because of the polarization, here you can see the negative charge is accumulated towards the positive side of the external electric field, and oppositely the other side is the positive charge itself is accumulated. And we learned that the electric field within the inside, so if you can draw within this entire inside the surface, the electric field equal to 0. So because this is the no charge region, so even though if the material is having certain cavity, even though the metal is having it's a cavity, so the electric field, the value inside the cavity, so if you can write the electric field inside the cavity goes to 0. If the electric field inside the cavity goes to 0, whatever the potential is remains constant. So what's the value of the potential is present within this material or within this surface, so the same potential will present. Suppose now if we keep a charge inside the cavity, so this is the case, a charge inside the cavity. Now closely if you can see it here, so inside the cavity the charge is a charge positive q is located inside the cavity. Now in this case let us see the charge distribution. Now if the charge, positive charge which is the present inside the cavity, now in the earlier case if there is no charge present inside the cavity, one side is negative charge and one side is a positive charge is accumulated. But if we can keep a charge within the cavity, now in this side, now this is a positive charge. Now since it is a positive charge, it will attract the negative charge. So the negative charge which is a close to this positive charge, so that will be accumulated on the inside surface of the cavity. So that is the key point at here. When we keep a charge inside the cavity, now in that case the nearby the electrons, because the negative charge only move within the conductors, positive charge cannot move. So the negative charge so already present within the conductor, so that will be accumulated inside the surface of the cavity. Now if the negative charge is accumulated inside the surface of the cavity, so what this positive charge does? And this positive charge will distribute uniformly. The positive charge will distribute uniformly throughout the metal surface. Now here you can see, when a charge is located within the cavity, the negative charge is accumulated on the inside the surface of the cavity and the positive charge is distributed throughout the outside surface. Now in this case also we were bound to this condition, the electrostatic field on the surface. If you can calculate the electric field within the surface, that value will becomes 0. Why? Because the positive charge and the negative charge, they both are the balanced at here. So how much charge you kept inside there, that much charge will be accumulated on the inside surface of the cavity. So that's why the electric field within the surface goes to 0. So this gives a very good examples how we save while thundering, or better to, there is a saying, perfect to say that. So while thundering, so it is safe to sit inside the car. So what could be the reason? So if you can sit inside the car while thundering, so the thundering is just like as a charge surface and car just like a cavity and we just like a charged force. So if you can take this person within the car as a conductor, human body is a conductor and the car is a conducting material. Now the whatever the charge is coming through the thunder, so in this case we are using a huge Van de Graaff generator to generate the positive charge. Now this charge will passes all the way through on the conducting surface and all over this car body. So it will be spread and it will be goes, here you can see closely at the front tire, so one small tiny spark. So this spark carries the entire the charges to the earth. Now in that case, the person who sat inside the car, so he is safe and sound. So this is the example for the electrostatic shielding. So here the car will be acts just like a cavity and whatever the charge, so carries by this the car surface, that leads to the electric field inside the car goes to 0. If the electric field inside the car goes to 0, it means the potential remains constant. So this is the key word. To get shock, there should be potential difference. If there is no potential difference, we cannot be electrocuted. So that's the reason, if you can see a bird, it can nicely sit on a live wire. Suppose if it's a bird, it can nicely sit on a live wire. So even though it will sit on the live wire in the electric post and all, if you can see, so it do not electrocuted. Why? Because it is sat on a same potential line. So there is no potential difference. Potential remains same. Suppose if you can see, the post do not carry a single wire, it carries doubles. One is live wire, one is neutral wire. If the bird wings extended and touch this neutral wire, if the bird wings extended and touch the neutral wire, now in that case the bird will be electrocuted, it will die. Why? Because here there is a huge potential difference will be there. Suppose it is carrying at the voltage of 220 volt and it's the neutral wire having the 0 volt. So what is the potential difference? Potential difference goes to 220 volt. So that's why the bird will be electrocuted in this case. So here inside the car, human beings are not electrocuted. So they are not getting the shock. Why? Because we are at the same potential. So potential is constant at here. Inside the car, potential is constant. Why the potential is constant? Because in this case, electric field inside the car equal to 0. If the electric field equal to 0, the potential remains constant. We are safe and sound. Now, how the charge is flowing from the car to the ground? Suppose this Van de Graaff generating at here, let me take as an 10,000 volt. So that is a great potential difference, and it is discharging to the air. So air is also gets tossed to conductor after certain voltage. Now it is discharging through the air. So now here the nearby the conductor, this is the car surface. Now that spark is finding the shortest path to the ground. Now the ground is having 0 potential. Now there is a potential difference, then only the charge will move. Charge always move from higher potential to the lower potential, just like water. How water flows from the high pressure region to low pressure region. So similarly, charge also moves from high potential region to the low potential region. So in this example particularly, so the person who sat inside the car, especially in the thunderstorms and all, so he will be safe because inside the car that acts like a cavity. So the charge within the cavity neutralizes, the entire electric field goes to 0, so there is no potential difference. So this is the concept regarding the electrostatic conductors. Suppose if you can take conductor, a charged conductor, what its properties. Now here I would like to highlight one more point, the charge density. So what it means, suppose if I take a conductor of like this or a conductor of like this. Now what we can define, they both are having the surface. So we can define electric field equal to sigma by epsilon naught. What the sigma you can call charge per unit area. The exact formula I can write sigma equal to Q by A. Surface charge density. Here n cap you can give the electric field direction. So that is the electric field directions. Now charge per unit area. Suppose if you can take a unit area at here, suppose if you can compare, so this is the unit area. So within area, if you can take what is the charge, how much is the charge, is only one charge is located. So to the surface too. Suppose if you can take the same, the unit area at here. Now in that location the charges at here will be more. Why? Because here you can see it's a sharp point shape, just like pen point shape. Now according to this formula, where the area is less, there the charge is more. So that is the relation, inverse relation. If the area is less and the charge is more, so that's the reason how the charge is uniformly distributes. If the charge is uniformly distributes on this cone shaped conductor or on this arch shaped conductor, so the charge has to distribute uniformly. Now the charge will occupies a location where there is a less area. So that's the reason all the lightning conductors, if this is a lightning conductor, so this lightning conductor should be pointed. So then only at here the more charge gets accumulated. If the more charge gets accumulated, so it will be attracted to the thunder. So why the lightning conductors are the point shape? So that is due to because of this is the reason. So why? The reason is that the charge density, the surface charge density, if the area is less, the charge accumulated by the conductor is more. So these are the properties we need to understand about. So if the conductor is in the electrostatics.